Problem Solving and Model Building 2. We're going to be looking now at representation, often via feature engineering and pre-processing, and quite often depending heavily on linear algebra. So let's review the similarity kernel. If k of xy is similar to x and y, then it's 1 only if x and y are identical. Closer to 1, the more similar x and y are. K of xy is always less than or equal to 1, and it's symmetric. For example, cosine similarity. K of xy is given by this, which is nothing more than the inner product over the norms, which of course defines the cosine. But similarity kernels tend to be too simple, so the data needs to be engineered until a kernel can produce good comparisons. In general, results are due to the data, not to the choice of a model. When we see that, when we look at our problem-solving process, in particular, our exploration now is going to be pre-processing via dimensionality reduction, and then we'll get representations in vector spaces as rectangular arrays, and then we'll move on to that in later modules. See, more data beats better model. Many papers, numerous studies have shown this. For us, we're going to say better data beats better model. Pre-processing and feature engineering are key. For example, 1,000 observations, binary labels, and I'm going to put the target as the first feature in the data. As you see here, the target's the first feature. But when I do my k-neighbors classifier with the original data, my best score is 50-50. About half, no better than random. But if I pre-process the data and then do the exact same model, which I've done here, then my score is perfect. Now our focus in this video is on the role of linear algebra in pre-processing. In particular because linear algebra can produce useful representations of the data, especially when such representations lead to dimensionality reduction, which we'll see in a few minutes. So in particular, suppose we are looking at data where we have samples or observations of variables. So we have a matrix where the columns of the matrix, bold A1 to bold AN, are M samples of variables, little a1 to little an. Sample covariance is the sample mean of these products of differences with the respective means. And this is from statistics, and this is a sample mean, an empirical mean. Our goal is a covariance preserving low rank approximation. Something that looks like this, where we choose D such that the ACE D equals DF approximation retains most of the covariance of the original. So if we have a matrix that is M samples of N feature variables, then there's actually a problem in approximating A with A sub D. For example, let's look at a truncated singular value decomposition. I'm using L here instead of D, but that's typical. L's the dimension of the latent space. And here's my A sub D. Now look at the means of the columns. They can differ significantly. So principal components analysis, we begin by noticing that if we have a matrix A and we have a set of ones, the ones vector, then 1 sub M transpose A is the row of column sums of A. Let me illustrate. Here's 1 sub M transpose of times A. So if I multiply by this ones vector, I get the sum of the first column. Similarly, I get the sum of the second column and the sum of the third column, and so on and so forth to the last column. So therefore, this 1 sub M transpose A is the sums of the columns. So if L is less than R, where R is the column rank of A, then the column sums can differ greatly between A and A sub L. But suppose that A is centered, and that centered version of A is what we are going to call X. In other words, X is where you subtract the column means respectively from the columns of A. That means that 1 sub m transpose x is equal to 0 because the column sums are all zeros. And remember, we had that x is equal to p sub r v sub r transpose, where v sub r transpose v sub r is the identity. So that means if x is p sub r v sub r transpose, then x v sub r is p sub r v sub r transpose v sub r, which is just p sub r I sub r, which is p sub r. Now, p sub r is x v sub r, which means 1 sub m transpose of p sub r is equal to 1 sub m transpose x v sub r. But notice that means we can use what's in the first line and we get zeros. In other words, centered data means we get centered components, which means that we preserve the column means because they're all zeros. So in summary, we have a matrix A, which is samples or observations of variables. That means our columns are in Rm, and Rm samples of variables A1 to An. We center that data. Now we have bold x1 to xn, which are centered. Their sum is 0. So these columns now sum to 0. The sample covariance coefficient, Cij, well, that's the sample average of the product of the variables xi and xj, which turns out to be 1 over m times the column xi transpose xj. And therefore, the covariance matrix, which is the matrix of these coefficients, is 1 over m times x transpose x. So if we use the singular value decomposition or the spectral theorem to write down what this looks like, then we have these squared singular values, and we choose d such that the sum up to d of the squared singular values is approximately the same as the sum up to the rank r of the squared singular values. And so we have our low rank approximation, our principal components analysis, where we have maintained that the sum of these squared singular values up to d is approximately the same as that up to r. And if we divide both sides by m, then we're actually looking at what's called explained variance. And as long as the explained variance is approximately the same for both, then the covariance of x is approximately the covariance of xd, which is p sub d v sub d transpose, because the data is centered. So this gives us a low rank approximation. Remember, the data has to be centered. But notice that this features is an orthonormal basis, which means we can use p in place of x. And the columns of p are sorted by variance in x in descending order. So the first column explains the most variance, and the second the next most, and so on and so forth. And so we get an approximation if d is less than the rank of x. And we can make d smaller and smaller as long as we retain most of the variance in x in the columns of p. In particular, if we can explain most of the variance with the first two columns of p, then all the data reduces to two-variable representation. So PCA is different than SVD. SVD is just where we apply this matrix decomposition. PCA is where we apply the SVD to centered data. And centering means we get squared singular values that are variances. And we can now choose a D that preserves most of the variance. So I'm just going to illustrate with just the first 5 observations of the exam data. Here's my A, here's my truncated SVD, and here's my A sub D. The column means are not the same. They could differ radically. But here is my centered version of A, and it's got column means of 0, and no matter how many components I use, I end up with my X sub D also has column means of 0. And the PCA commands that we use always center the data first. So we don't actually have to center ourselves. The command will do it for us. For example, we had this problem with the arbitrary feature selection when we did logistic regression and got a decision surface for our exam data. But why did we just use exam 3 and 4? What about exam 1 and exam 4? Well, this arbitrary selection is rarely justified. But dimensionality reduction to 2 dimensions is justified if most of the variance is preserved. So here's our original representation of the exam data. We do a principal components analysis, and we get a latent space representation. Then we look at the explained variance ratios, and we notice that when we add those up, we get 85%. In other words, the first two components explain 85.6% of the total variance in the data. And therefore, we get this latent space representation, which is as good as using all 5 of the original features. And notice how illustrative it is. We almost have separable data. So the grades data has 5 features, but most of its variance is explained by the first 2 components. Logistic regression on the first 2 components, L1 and L2 as the labels of those, looks like this. All the data, but it's reduced to a 2-dimensional latent space. And remember, of course, that we had to center the data before we did this. So we are here pre-processing via dimensionality reduction. We're getting a vector space representation as rectangular arrays of our original data. And our focus is currently on representation. However, K&N methods and many other methods are often improved when we have improved representations of the data. For example, let's look at the IRIS dataset. In 1936, Sir Ronald Fisher came up with the IRIS dataset, 50 samples in each of 3 classes, 4 features, sepal length, sepal width, petal length, and petal width. So the data looks something like this. And notice it's easy to distinguish isotosa from the other 2. Now, using only 2 features, sepal length and sepal width, we end up with this representation. It should be really easy to see the difference between setosa and the others. It is in real life. The neighbors predict a class of an unlabeled XY. In this case, predicted to be setosa. In this case, predicted to be virginica. And we can do this for every possible point. We get a coloring of the XY plane. This is what's known as a decision model. And the plot of this decision model is called a decision surface. And the boundaries are called decision boundaries. But there are issues. So notice that we really don't know what to do with some of these points because they're right where the boundaries are. And look at these kind of little island boundaries in the blue region. So a better approach is to use more features. We only use 2 here. So to illustrate, let's look at some Python code. I'm going to use a k-nearest neighbors classifier, and I'm also going to use grid search CV. What that does is it allows me to find the best parameters among a set of given parameters for my k-nearest neighbors classifier over multiple folds of the data. So where folds means we use one fold as the testing data and the other remaining as the training data, and we do that over multiple folds. So it's going to find the best K as it does this cross-validation. And here we're only using 2 features. And notice that the very best we can do is 80% accuracy using 7 neighbors. But now let's do a principal components analysis. And notice that the explained variance, the first 2 components explain 97.7% of the variance. So let's look at what that looks like. Here is my latent space representation. Notice that setosa is far from the other 2, which is what happens in real life. And we can almost split the other 2 species themselves. So when we redo our grid search using the principal components, the latent space representation, I'm not using metric equals cosine, and I'll explain why on the next slide. But this latent space representation, as the data that we fit to, gives me a best accuracy of 97.3% using only 3 neighbors. That means the model is less biased. And then I'm going to use this code down here to produce what's on the next slide. So here is what we get if we only use sepal width and sepal length. In other words, only 2 features and only 80% accuracy. But here is what we get when we do our latent space representation. And we get 97.7% accuracy. We're using all the features, even though it's only a 2-dimensional representation. Now here's what happens when you do metric equals cosine, and so I didn't want to do that. Now let's look at another aspect of this matrix decomposition, low rank approximation, called non-negative matrix decomposition. So if I have a matrix X and all the coefficients of X are greater than or equal to 0, then I'm just going to simply write the matrix X is greater or equal to 0. So X greater or equal to 0, all its coefficients are non-negative. And if X is a non-negative matrix, then we can also often write it as the product of non-negative matrices. In other words, our old data can be approximated by new data times the features where all 3 are non-negative matrices. And this is called non-negative matrix factorization. Once again, we have latent variables, and we often choose D as small as we can while preserving our information. So the iris data is non-negative. So let's apply non-negative matrix factorization. As you can see here, it's no more difficult to apply than principal components. And now I redo my grid search CV on my latent space representation using non-negative matrix factorization, and my best accuracy is 98%. And here is my non-negative matrix latent space representation. So kernels for nearest neighbor methods. You see, when nearest neighbors methods work well, it's because the similarity kernel did the heavy lifting. But that means we really have to help out that kernel by getting a lot of preprocessing. And we have to map our observations to Rn, and we need those to be good representations. And we then have to construct a kernel that's faithful to the true model. That's actually very hard, as you'll see in the next video. But this means that the kernel needs very good data representations to get suitable and appropriate similarity measurements. The cursive dimensionality is often an issue, but working in 2 dimensions is easy to interpret. And perhaps most importantly, linear algebra plays a key role in preprocessing in particular and in feature engineering in general.